Hello my friends and welcome back to the You Can Do TV channel. The Caterpillar Oil and Gas Facility in Lafayette operates as a highly controlled, process-driven manufacturing site dedicated to large engine assembly and validation. Production begins in the assembly area, where engine blocks undergo precision machining and dimensional verification to ensure alignment with Caterpillar's strict tolerances. Each engine block is subjected to dedicated testing before moving forward, eliminating defects early in the workflow. Crankshafts follow an independent test process, including dimensional inspection, surface integrity checks, and balance verification. Robotic rod machining ensures consistent geometry, accurate bore alignment, and repeatable quality across all connecting rods. Once approved, the crankshaft is installed using smart tooling systems that control torque, positioning, and sequence, significantly reducing human error. Piston and rod installation is performed with guided assembly systems that monitor insertion force and orientation, ensuring optimal fit and long-term durability. For larger platforms, including the 3600 series, crankshaft installation is carried out using specialized lifting and alignment equipment designed for heavy-duty components. Every engine assembled at the Lafayette facility undergoes comprehensive on-site testing. These tests simulate real operating conditions, verifying performance, pressure stability, vibration levels, and emissions compliance. After successful validation, engines move through a robotic paint process that delivers uniform coating thickness and corrosion protection. The final stage includes preparation for shipment and detailed inspection, covering documentation, visual checks, and protective packaging. This end-to-end technology-driven process ensures Caterpillar oil and gas engines meet the highest standards of reliability, safety, and operational performance before reaching global customers. Inside Cummins, this is Jamestown, focuses on the technical foundation of heavy-duty engine manufacturing at the Jamestown engine plant. The facility applies advanced machining, digital control systems, and tightly regulated assembly processes to produce ISX-15, X12, and X12 natural gas engines with high reliability and long service life. Manufacturing begins with in-house machining of critical components, including CGI cylinder blocks, cylinder heads, camshafts, and flywheels. These parts are produced using high-precision CNC machines, with key parameters such as bore geometry, surface finish, and positional accuracy controlled to micron-level tolerances. Continuous in-process measurement and operator verification ensure dimensional stability and structural integrity. Assembly is performed on two flexible, high-speed lines. Each engine is built to order, with more than 400 components installed under full electronic traceability. DC torque tools, automated verification systems, and interlocks prevent process deviations, ensuring every fastener and component meets specified torque and sequence requirements. The engine cannot advance unless each operation is validated, eliminating assembly errors. Fuel systems, turbochargers, and EGR components are installed in controlled, clean environments to protect performance and emissions compliance. Every completed engine undergoes full functional testing, including idle simulation, acceleration ramps, and full load fueling checks to verify output, efficiency, and durability. On-site engineering, testing laboratories, and mobile diagnostic units support continuous product improvement and real-world performance validation. This integration of precision machining, data-driven assembly, and comprehensive testing defines Jamestown as a benchmark facility for technically robust, heavy-duty engine production. Inside the Cummins mid-range engine plant, advanced manufacturing systems, disciplined processes, and skilled personnel come together to produce the Cummins 6.7-liter turbo diesel engine. This facility was designed to establish a new benchmark for durability, reliability, efficiency, and long-term performance in the truck industry. Production begins with a compacted graphite iron (CGI) engine block, machined in-house to extremely tight tolerances. Precision machining ensures optimal alignment for critical components such as the crankshaft, camshaft, and pistons, forming a robust foundation capable of supporting service lives exceeding 1 million miles. Automated and semi-automated stations control dimensional accuracy at every stage of assembly. Turbocharger installation is a critical operation. Each turbo is precisely aligned and matched to its engine to maximize airflow efficiency, boost response, and overall power output. The fuel system incorporates heavy-duty diesel technology, with injectors installed in a tightly controlled, dust-free environment to ensure consistent combustion, fuel economy, and emissions performance. The exhaust gas recirculation (EGR) system is assembled on a dedicated line, where each component is fitted with exacting precision. This contributes to near-zero knock characteristics and significantly reduced particulate emissions. Throughout the production line, engines undergo continuous inspections, measurements, and functional checks. Every completed engine is fully tested before leaving the plant. Highly trained teams, certified across multiple processes, are empowered to halt production if any quality issue arises. This integrated approach ensures each Cummins 6.7 engine meets the highest standards and is truly built to last. The PACCAR engine plant in Columbus, Mississippi, operates as a fully integrated manufacturing facility dedicated to the production of high-performance diesel engines. The process is organized around a clear, technically controlled workflow that ensures precision, consistency, and durability at every stage. Production begins in the block machining area, where raw cast engine blocks are processed using advanced CNC machining centers. Critical features such as cylinder bores, bearing saddles, oil galleries, and mounting surfaces are machined to tight tolerances and verified through in-process measurement systems. In parallel, cylinder head machining focuses on valve seats, ports, and combustion surfaces, ensuring accurate airflow, sealing performance, and thermal stability. Once major components are completed, they move to the engine assembly line. Here, crankshafts, pistons, connecting rods, camshafts, and valve train components are installed using torque-controlled tools and automated verification systems. Each assembly step is monitored to maintain correct sequencing and specification compliance. Following assembly, engines undergo calibration and functional testing to validate power output, emissions performance, and operational stability. Approved engines are then painted using automated coating systems for corrosion protection and visual consistency. Finally, completed engines are prepared for shipping, with full traceability and quality documentation, ready for global distribution. The MAN engine portfolio encompasses a broad range of industrial and power generation engines engineered for efficiency, durability, and application-specific performance. In the power generation segment, MAN gas engines are designed for continuous and peak load operation with natural gas and special gases such as biogas or landfill gas. These engines deliver high overall thermal efficiency beyond 90% and are optimized for reliability in power plants, cogeneration systems, and distributed energy applications. They support security of supply and robust field performance across utility, commercial, and industrial environments. MAN's product range also includes industrial gas turbine technology for power generation and mechanical drive applications. A gas turbine operates by compressing air, mixing it with fuel, and combusting this mixture under constant pressure. The resulting hot gas expands through turbine stages that drive both the compressor and output shaft, enabling electrical generation or mechanical work. Industrial gas turbines like the MGT series provide modular, high-efficiency solutions in the 6 megawatts to 8 megawatts range, balancing emissions performance with compact design and operational flexibility. Whether configured for continuous duty in power networks or dynamic industrial environments, MAN engines are engineered to meet stringent reliability and efficiency standards demanded by modern energy infrastructure. At Matsuura Shipyard, the construction of the new coastal cargo vessel Daiichi Fukuyoshimaru, hull number 602, reaches a critical milestone with the installation of the reversing gear and main engine. This stage represents one of the most technically demanding operations in the shipbuilding process, requiring precision alignment, controlled lifting, and strict quality management. The operation begins with the positioning of the reversing gear or reduction gearbox, which plays a vital role in transmitting power from the main engine to the propeller shaft while enabling a head and a stern operation. The unit is carefully lowered into the engine room, using overhead lifting equipment, with alignment checked continuously against the shaft centerline. Precise leveling ensures optimal load distribution, vibration control, and long-term reliability during service. Following the successful installation of the reversing gear, attention shifts to the main engine. The marine diesel engine is transported into position as a single integrated unit, reflecting Matsuura Shipyard's emphasis on efficiency and accuracy. During lowering, clearances between the engine, foundation, and surrounding structures are monitored in real time. Once seated on the engine bed, fine alignment adjustments are performed to achieve exact concentricity between the crankshaft, coupling, and reversing gear input shaft. Foundation bolts are then installed and tightened according to specified torque values, securing the engine and gearbox assembly firmly to the hull structure. This step is essential to withstand continuous operational loads and marine vibration. After mechanical fixing, preliminary checks are conducted on shaft alignment, bearing clearances, and coupling fit. The installation phase concludes with preparation for auxiliary connections, including lubrication lines, cooling water circuits, fuel systems, and control linkages. These interfaces ensure seamless integration of the propulsion system with onboard machinery and navigation controls. This carefully executed process demonstrates Matsuura Shipyard's shipbuilding expertise and commitment to technical excellence. By ensuring precise installation of the reversing gear and main engine, Daiichi Fukuyoshimaru is equipped with a robust, efficient propulsion system designed to meet the demanding requirements of Japan's coastal shipping operations, delivering reliability, maneuverability, and long-term operational performance. The Art of the Motor offers an inside look at the people, craftsmanship, and passion behind every Indian motorcycle engine. From precision engineering to hands-on dedication, the team at the Osceola, Wisconsin plant brings each engine to life with pride and expertise. This process reflects more than manufacturing. It represents a deep respect for heritage and performance. Founded in 1901, Indian Motorcycle is America's first motorcycle company, renowned for legendary racing success, engineering excellence, and groundbreaking innovation. Today, that rich legacy continues under new stewardship, reigniting the spirit that has inspired motorcyclists around the world for generations. Have you ever wondered how a truck really works? At Volvo Trucks, diesel engine manufacturing plant in Skövde, Sweden, the story of a heavy-duty engine begins with precision casting and advanced industrial control. Spread across 265,000 square meters, this facility produces around 72,000 engines each year and stands at the core of Volvo Group Trucks operations. Inside the foundries, molten iron is shaped into engine blocks and cylinder heads using highly refined casting techniques. In the state-of-the-art G2 foundry, water-cooled molds accelerate solidification, increasing material strength while allowing water to be recycled in a closed loop. Heat generated during casting is partially recovered and reused, and most of the molding sand is reclaimed, reflecting Volvo's strong commitment to sustainable production. Before casting, robotic systems assemble complex core packages with millimeter-level accuracy. These cores are coated with a special refractory layer to ensure flawless internal surfaces. Once the castings cool, they move into automated machining lines, where engine blocks, cylinder heads, crankshafts, and camshafts are machined and measured to tolerances as fine as 1/1000th of a millimeter. In the assembly hall, components come together to form complete engines, such as the 13-liter D13. Each engine is briefly run for its first start, with critical parameters continuously monitored. After passing inspection, the engine is painted, prepared for shipment, and sent to vehicle assembly, ready to power Volvo trucks for hundreds of thousands of kilometers. Wing's 14RT Flex 96C, formerly developed under Wärtsilä, stands as the most powerful diesel engine ever built for marine propulsion. Manufactured by Doosan Engine Co. In South Korea, this low-speed two-stroke engine was engineered specifically for ultra-large container ships carrying up to 16,000 TEU. With an extraordinary 14-cylinder inline configuration, the engine measures 26.6 meters in length and weighs approximately 300 tons. Each cylinder features a 96 centimeters bore and a 250 centimeters piston stroke, operating at 102 revolutions per minute and delivering 5,720 kW per cylinder for a total output of 8008 kW. This immense power enables vessels to reach speeds of up to 27 knots. Building on this legacy, Winged introduced the X92 series, designed for the next generation of ultra-large container vessels, offering higher efficiency, larger stroke dimensions, and improved power density. At the Indian Motorcycle Assembly Facility in Spirit Lake, Iowa, production follows a highly controlled, technician-driven manufacturing process. All motorcycles are assembled manually, allowing precise control over component fitment, alignment, and torque application. Each subsystem, engine, drivetrain, chassis, electrical, and bodywork, is installed sequentially and verified at dedicated workstations. Paint operations comply with strict surface preparation, coating thickness, and curing specifications to ensure durability and corrosion resistance. In-process inspections are performed continuously, with technicians responsible for dimensional accuracy and functional compliance. Final quality checks validate mechanical integrity, finish consistency, and operational performance. This hands-on assembly approach ensures every motorcycle meets stringent engineering standards for reliability, structural integrity, and long-term service life. After sitting idle for 3 to 4 years, the 6-71 Detroit diesel marine engine was brought back to life on a cold morning following a -10°C night. By midday, temperatures had improved, allowing preparations to begin, fuel delivery restored, and a squirrel's nest cleared from the exhaust. After several cranks, the engine roared to life. The process required juggling multiple tasks, as the hydraulic governor lacks an idle setting, meaning the throttle needed to be manually fixed open. Despite the challenges, the startup marked a successful return to operation for this classic marine power plant. Diesel House in Copenhagen is an industrial museum and experience center showcasing Denmark's rich diesel engine heritage. A highlight is the B&W locomotive No 2000, a preserved example of Burmeister and Wain's engineering excellence. Visitors can also see B&W Locomotive No. 1, the pioneering model that marked the company's entry into locomotive production, alongside the Holby Locomotive No. 1 and the Burr-Wain locomotive. These machines illustrate the evolution of diesel technology in Danish rail transport. Designed for durability and efficiency, each locomotive represents a chapter in industrial history, offering students a hands-on look at mechanical innovation and engineering progress. GE Aviation's engine overhaul shop in Brazil showcases advanced processes, including design engineering, moving line hub and machine head operations, nacelle loading in Salzburgen, and turbine installation and commissioning in Uflead. This facility ensures precision and efficiency in engine maintenance and refurbishment for optimal performance. The Hyundai Sulzer 12 RTA 96C is a two-stroke, turbocharged, low-speed diesel engine designed for large container ships. Operating at 72 RPM, it delivers approximately 640 kilowatts, 92,000 bhp of power. Each of its 12 cylinders has a bore of 960 millimeters and a stroke of 500 millimeters. The engine's total length is about 23.2 meters, and it weighs approximately 2,030 tons. It is designed to run on heavy fuel oil and is optimized for fuel efficiency and low emissions. The engine's design includes features like a crosshead bearing system and electronically controlled exhaust valves to enhance performance and reduce maintenance needs. This engine is commonly used in large container ships, providing reliable and efficient propulsion. At Nucor Steel Decatur, modern steelmaking is driven by precise chemistry, advanced technology, and an efficient recycling-based process. Production begins in the scrapyard, where multiple grades of scrap steel are carefully sorted and blended to meet exact customer specifications. This engineered scrap mix is charged into 200-ton electric arc furnaces, where high-power electrical energy melts the material at temperatures approaching 3,000 degrees Fahrenheit. Compared with traditional blast furnaces, this method delivers significantly higher energy efficiency and a lower environmental footprint. The molten steel is transferred to the ladle metallurgy furnace, where its chemical composition is fine-tuned. Elements such as carbon, manganese, titanium, and columbium are adjusted with extreme accuracy to achieve the required mechanical properties, including strength, toughness, and low-temperature performance. Once refined, the steel is continuously cast into slabs, marking the first solid form of the product. These slabs are reheated and passed through high-pressure rolling mills, where thickness is precisely reduced at high speeds. The steel is then finished, galvanized if required, and coiled for shipment. From scrap to finished coil, the entire process takes only a few hours, delivering high-quality steel engineered for demanding applications. General Motors' 6271L diesel engine roars to life during testing. Its inline-six design delivering legendary reliability, smooth power, and the unmistakable growl beloved by classic machinery enthusiasts. The Detroit diesel marine engine roars to sequence. Known for its reliability and power, this two-stroke diesel engine is a favorite in marine applications, delivering strong performance even after long periods of inactivity. The Kawasaki Ninja H2R on the dyno is a pure symphony of mechanical fury. Powered by a supercharged 998cc inline-4 engine, it delivers an astonishing 310 horsepower, climbing to 326 horsepower with ram air. On the test bench, the supercharger's whine merges with the deep exhaust roar, pushing the bike's performance envelope in a controlled environment. Engineers monitor boost pressure, air-fuel ratios, and engine temperatures as the H2R surges toward redline at over 14,000 revolutions per minute. Designed for closed-course use, this machine's aerodynamics and power output make it one of the fastest production motorcycles in the world. The dyno run showcases the H2R's brutal acceleration and engineering mastery, proving its dominance in high-performance motorcycling. The Kawasaki Ninja H2 roars into the Bonneville Salt Flats, aiming to break records with sheer power and precision. At the heart of this beast lies a supercharged, producing over 300 horsepower, a true marvel of engineering designed for speed and endurance. Running continuously at maximum load, the engine faces extreme stress, pushing both metal and rider to their limits. The track is far from forgiving. Deep ruts, sharp holes, and sticky mud-like patches challenge every inch of grip and balance. Each mile is meticulously timed, demanding 2 consistent, high-speed runs to set a new record. The team fine-tunes throttle and traction control, balancing the Ninja H2's immense power with razor-sharp handling. After 3 trials on the changing salt surface, the team recorded a best run of 207.263 miles per hour, 333.557 kilometers per hour. This attempt isn't just about speed, it's a testament to Kawasaki's relentless pursuit of innovation, blending cutting-edge engine technology with the raw determination of a team ready to conquer nature's toughest challenges. Every twist of the throttle and every second on the salt flats brings them closer to motorcycle legend. Union Pacific Big Boy 4014 departs San Antonio, Texas on November 6, 2019, its massive steam power and deep whistle echoing as the world's largest operating steam locomotive begins its journey. The Bluebird K7's heart is a Bristol Siddeley Orpheus 701 turbojet engine, the same type used in the Folan Nat fighter aircraft. Producing around 500 pounds of thrust, it enabled the hydroplane to skim the water at extreme speeds. During startup, the Orpheus emits a high-pitched whine as the compressor spools up, followed by the powerful roar of combustion as fuel ignites. The exhaust blasts from the rear nozzle in shimmering heat waves, while the engine's steady surge of thrust readies the craft for its high-speed runs, embodying the raw power and precision of 1960s jet engineering. The Bluebird K-7, Donald Campbell's iconic jet-powered hydroplane, made its poignant final run on Lafayette, Butte, in a fitting farewell to a machine that once redefined speed on water. Built in 1955, the K-7 was powered by a Bristol Siddeley Orpheus turbojet, producing around 500 lb-f of thrust, enabling Campbell to set 7 world water speed records between 1955 and 1964, with a peak speed of 444.71 kilometers per hour on Lake Dumbleyung, Australia. Restored after its fatal crash on Coniston Water in 1967, the craft returned for public demonstrations, allowing new generations to experience its engineering brilliance. On Lafayette, the K-7's final outing saw crowds lining the shores, the air filled with the scream of its jet engine and the spray of its passage. This last display honored Campbell's fearless pursuit of speed, ensuring the Bluebird K-7's legacy as a masterpiece of British engineering and human ambition. Feel the ground tremble as the Shockwave jet truck explodes into motion, blasting down the runway at a heart-stopping 375 kilometers per hour. 3 roaring Pratt & Whitney J34-48 jet engines, once meant for the skies, now unleash 36,000 horsepower and 21,000 pounds of thrust on asphalt. Fire and thunder erupt from its tailpipes, the air vibrating with raw energy. It's not just speed, it's a living storm of metal, power, and pure adrenaline, rewriting what it means to go fast. Meet the Shockwave jet truck, a gigantic semi that's anything but ordinary. Powered by not 1, not 2, but 3 Pratt & Whitney J34-48 jet engines. Originally built for military planes, this beast roars with a combined 36,000 horsepower and 21,000 pounds of thrust. This incredible power propels the truck to speeds exceeding 350 miles per hour, or about 563 kilometers per hour. Shockwave holds the world record as the fastest large jet-powered truck, reaching a top speed of 376 miles per hour, roughly 605 kilometers per hour. This beast on wheels is truly a jaw-dropping example of engineering pushing the limits of speed and power. The Pratt & Whitney R-4360 Wasp Major stands as the largest displacement piston aircraft engine ever mass-produced in the United States. Introduced in 1944, this air-cooled 4-row radial engine features an unconventional 28-cylinder corncob configuration, designed to deliver unmatched power for heavy aircraft in the final years of the piston era. With a displacement of 362 cubic inches, 71.5 liters, it produced between 500 and over 300 horsepower depending on the variant, driving some of the most ambitious propeller-driven aircraft ever built. Each row of cylinders is staggered for optimal cooling, with a master and articulating rod system managing the complex crankshaft arrangement. The R-4360 employed a supercharger for high-altitude performance, and in some applications, water injection was used to boost takeoff power. At over 3 meters in diameter and weighing around 3,870 pounds, 1,755 kilogram, this mechanical giant required meticulous maintenance and precise operation to deliver peak performance. The R-4360 powered legendary aircraft such as the Boeing B-50 Superfortress, Convair B-36 Peacemaker, and Douglas C-124 Globemaster II, bridging the gap between piston propulsion and the emerging jet age. Its immense power output and engineering complexity cemented its reputation as a pinnacle of radial engine design, representing the height of World War II-era piston technology. The first run of the R4360-powered Hawker Sea Fury racer, nicknamed Furious, marked an exciting milestone in aviation history. Equipped with the powerful 28-cylinder Wright R4360 radial engine, this racer delivers extraordinary horsepower and speed. The engine's distinctive roar and immense power promise thrilling performance on the racetrack. Furious showcases engineering excellence and the spirit of post-war air racing, pushing the limits of piston engine aircraft design and capability. GE Aviation's engine overhaul shop in Brazil handles over 300 engines annually. Upon arrival, engines undergo initial inspection and disassembly for cleaning and detailed defect detection, including wear and cracks. Engines consist of 3 modules: fan, core, and turbine, with over 12,000 parts. Necessary repairs are identified and performed using specialized techniques depending on materials. After roughly 35 days, components are reassembled, followed by rigorous testing on a test bench simulating real flight conditions. GE Aviation on-wing support delivers expert technical maintenance directly on aircraft worldwide. Using advanced diagnostics, rapid repairs, and OEM-certified technicians, it minimizes downtime and ensures engine reliability. Repair services include quick engine changes, module repairs, bore scope inspections, on-wing maintenance, and repairs to avoid unscheduled engine removals. The GE 90-115B, the world's most powerful jet engine, awakens with a deep, resonant growl as it powers up on a Boeing 777F cargo aircraft. Its massive 128-inch fan begins to spin, pulling in air with a thunderous roar. Designed for long-haul efficiency, this engineering giant produces up to 127,900 pounds of thrust, effortlessly lifting fully loaded freighters across continents. From startup rumble to full power, the GE 90-115B is a breathtaking blend of brute force and refined aerospace innovation. On August 15, 2018, the Sanders Sea Fury took to the skies for a thrilling test flight, piloted by Dennis in a high-performance lap around the course. This Hawker Sea Fury, originally a late World War II Royal Navy fighter, has been extensively modified for air racing, boasting a powerful Pratt & Whitney R-3350 radial engine, delivering well over 3,000 horsepower. The long-cut flight allowed to push the aircraft through smooth, sweeping turns and straight-line bursts, testing engine performance, propeller response, and cooling efficiency under race-like conditions. The distinctive roar of the R-3350 echoed across the airfield as the Sea Fury sliced through the sky with incredible speed and agility. Such test flights are vital for fine-tuning handling, verifying engine reliability, and ensuring peak performance before competitive runs. Your content Tacker Relas. The Union Pacific Big Boy 4014 the world's largest operating steam locomotive, made a striking appearance in Elmhurst, Illinois. Built in the 1940s for hauling heavy freight over the Wasatch Mountains, this 1.2 million pound giant stretches over 132 feet and boasts a 488 four-wheel arrangement. Restored to operating condition in 2019, it now tours the country as a living piece of rail history. In Elmhurst, crowds gathered trackside to witness its thunderous approach, the deep chuff of its pistons, and the billowing steam plume, a nostalgic reminder of the golden age of American railroading. Union Pacific Big Boy 4014, the world's largest operating steam locomotive, departs San Antonio in a cloud of steam and thunderous chuffs. Its massive 488 four-wheel arrangement and over 6,000 horsepower propel it forward, showcasing the raw power and historic grandeur of America's railroading past. WEG's synchronous condenser project represents a significant achievement in heavy electromechanical manufacturing. In Brazil, WEG produced two of the largest synchronous condensers ever built in the country, each weighing 310 tons, 7 meters in height, and 11 meters in length, marking a milestone in engineering and industrial capability. The manufacturing process of WEG's compensator Synchrono begins with the engineering design phase, where requirements for reactive power, voltage stability, and system inertia are translated into an optimal electromechanical configuration. Engineers meticulously simulate electrical characteristics, mechanical applications, and thermal conditions to ensure stable operation of the device in high-power transmission networks. The manufacturing process for such large synchronous condensers begins with heavy structural fabrication. Massive stator and rotor assemblies are engineered and machined to stringent tolerances, ensuring mechanical balance and robust electromagnetic performance. The stator core is constructed from high-grade electrical steel laminations designed to reduce core losses and maintain uniform flux distribution. The rotor assembly is precision balanced to handle high rotational speeds and significant centrifugal forces during operation. Cooling systems, bearings, and excitation circuits are also built into the assembly at this stage to support reliable long-term operation. Because of their size and complexity, these condensers require heavy-duty lifting equipment and precise alignment procedures during assembly. After completion, these machines are prepared for transport and installation at high-voltage substations, where they will serve critical roles in grid support and voltage control. The automatic washing machine motor production line developed by Suzhou Smart Motor Equipment Manufacturing Co., Limited, is designed for high-efficiency, large-scale stator manufacturing with consistent quality. The process starts with a paper inserting machine, which accurately places insulation paper into the stator slots to ensure electrical isolation. A high-speed coil winding machine then produces precisely wound copper coils with uniform tension and turn count. These coils are transferred to a coil inserting machine, where they are accurately positioned into the stator core. A lacing machine secures the windings, improving mechanical strength and vibration resistance during motor operation. The forming machine shapes the coil end turns to achieve standardized geometry and optimal fit within the motor housing. Finally, integrated testing machines perform electrical and insulation checks, verifying resistance, continuity, and dielectric strength. This half-automated line enhances productivity, reduces labor dependency, and ensures reliable motor performance for modern washing machine applications. The manufacturing of electric rotating machines at TES follows a precise and fully integrated industrial workflow. Production begins in the laminations department, where high-quality electrical steel sheets are punched and stacked to form stator and rotor cores with optimal magnetic efficiency. These cores move to welding, where structural rigidity and dimensional stability are ensured. Toolmaking and machining play a central role, producing precision dies, fixtures, shafts, and housings with strict tolerance control. Each machine component then passes through a detailed checkup stage, where geometry, alignment, and surface quality are carefully verified. In the winding and assembly area, coils are accurately wound, insulated, and inserted before the complete machine is assembled with exact mechanical balance. Every unit is then tested in the test field for electrical performance, vibration, and thermal behavior. Finally, the machines are painted for long-term protection and prepared for dispatch, ready for dependable industrial operation. Inside one of the most advanced electric motor factories of 2025, production is driven by high-precision automation and data-controlled manufacturing systems. At the core of the process are next-generation winding machines, capable of ultra-accurate coil placement with micron-level consistency. These machines automatically control wire tension, winding speed, slot filling rate, and insulation integrity to ensure optimal electromagnetic performance. Stator and rotor production is fully synchronized with digital quality monitoring, allowing real-time detection of defects and parameter deviations. Advanced sensors, vision systems, and inline testing verify resistance, insulation strength, and dimensional accuracy. This tightly integrated winding and assembly process delivers electric motors with higher efficiency, reduced losses, improved thermal performance, and long-term operational reliability. The AMOT electric motor manufacturing process at Abana Motor follows a structured and tightly controlled workflow. It begins with raw material selection, including electrical steel laminations, copper wire, and insulation components. Stator cores are precisely stacked and wound using automated winding machines to ensure uniform electromagnetic performance. Rotor assemblies are dynamically balanced to minimize vibration. After assembly, motors undergo impregnation, curing, and thermal treatment to enhance insulation durability. Each unit is then fitted with bearings, housings, and cooling systems. Final stages include electrical testing, load performance checks, and quality. PRG International Electricals Private Limited operates a highly integrated and technology-driven manufacturing process focused on electrical stampings, laminations, wound stators, die-cast rotors, and aluminum die-cast components. The workflow begins with precision tooling developed in the in-house tool room, ensuring dimensional accuracy and repeatability. High-grade electrical steel is processed through advanced notching machines and automated power presses to produce laminations with tight tolerances and minimal material loss. These laminations are stacked, insulated, and assembled into stator cores, followed by automated copper winding to achieve consistent electromagnetic performance. Rotor manufacturing includes aluminum die casting, machining, and dynamic balancing to ensure mechanical stability and efficiency. Throughout production, rigorous in-process inspections and testing systems monitor quality at each stage. With an annual capacity of approximately 35,000 tons of laminations, the facility continuously upgrades infrastructure and machinery in line with international standards. Supported by a skilled technical team and ongoing R&D initiatives, PRG delivers scalable production, reliable quality, and products suitable for both domestic and global electrical equipment markets. At the heart of the GE9X lies an advanced engine core where extreme pressure, temperature, and precision converge. Designed to push the boundaries of modern aviation, this core integrates a high-pressure compressor, an advanced combustor, and a highly efficient turbine, all working in perfect harmony. The compressor delivers an unprecedented pressure ratio, maximizing airflow efficiency and preparing the air for clean, stable combustion. Inside the combustor, fuel and air mix with remarkable precision, producing intense energy while significantly reducing emissions. This energy is then transformed by the turbine into powerful rotational force, driving the massive fan and propulsion system. Together, these components enable the GE9X to achieve record-breaking thrust while maintaining exceptional fuel efficiency. The result is an engine that sets new standards for reliability, performance, and sustainability. Purpose-built for the Boeing 777X, the GE9X represents a new generation of jet engine technology, delivering quieter operation, lower operating costs, and unmatched long-haul capability for the future of commercial aviation. Aerospace engineering is a highly technical discipline focused on the analysis, design, and optimization of aeronautical and space systems. The profession emphasizes rigorous engineering fundamentals, including advanced mathematics, physics, and systems engineering, applied to complex aerospace applications. Aerospace engineers are trained to design and model structural components using specialized CAD and CAE software, perform structural, thermal, and fluid dynamic simulations, and validate performance through analytical and numerical methods. Core technical areas include aerodynamics, thermodynamics, propulsion systems, flight mechanics, avionics, and control systems. Engineers develop and integrate propulsion units, navigation and communication systems, and onboard control architectures while ensuring compliance with strict aerospace standards and safety regulations. Materials engineering also plays a critical role, with a focus on composites, high-temperature alloys, and lightweight structures optimized for strength, durability, and efficiency. Manufacturing processes such as precision machining, additive manufacturing, and composite layup are combined with quality control and testing methodologies. At UABC, the Aerospace Engineering program builds strong technical competence through foundational engineering courses, followed by specialized training in propulsion, aerodynamics, instrumentation, satellites, and aerospace manufacturing, preparing graduates for technically demanding roles in the aerospace industry. GE Aviation's Passport Engine Certification and Testing Program focuses on validating performance, durability, and compliance with stringent aviation standards. The engine core, derived from the LEAP architecture, undergoes extensive ground testing before flight readiness. Development testing is conducted across multiple facilities, from Ohio to Winnipeg, covering thermal performance, mechanical integrity, and operational reliability. These tests verify thrust capability, fuel efficiency, and system robustness, ensuring the Passport engine meets certification requirements prior to its first flight. The first full GE9X engine, developed to power the Boeing 777X, is transported to the test stand at GE Aviation's Peebles test operation in Ohio. This milestone marks the transition from assembly to full-scale validation, enabling comprehensive testing of thrust, structural integrity, and system performance under controlled conditions. The TESS Salient Pole Rotor Winding Machine, designed and manufactured by TESS v. Seton SRO, is an in-house engineered solution for high-precision winding of generators and electric motor rotors. The machine supports salient pole rotors with 4 to 20 poles, offering exceptional flexibility for different power ratings and designs. Built for heavy-duty industrial operation, it ensures accurate conductor placement, consistent tension control, and repeatable winding quality. TESS provides both custom machine supply and contract rotor winding services. GE applies digital engineering by integrating Salesforce with industrial data systems to connect people, processes, and machines. Real-time machine data, analytics, and secure networks enable predictive maintenance, coordinated service operations, and data-driven decision-making, improving reliability, efficiency, and lifecycle management across complex industrial assets. This is Caterpillar, where a complete range of heavy machinery is engineered and built to work in the toughest environments. From excavators, bulldozers, and wheel loaders, to mining trucks, engines, and power systems, every machine is designed with advanced technology, robust structures, and proven reliability to deliver maximum productivity worldwide. Cummins Foundry Inc. is a specialized foundry and machining facility that produces high-quality castings using advanced technologies. They utilize styropor patterns for casting production and have a semi-automatic molding line, capable of producing 30 molds per hour with an annual output ranging from 500 to 10,000 pieces. The foundry operates two 6-ton middle-frequency induction furnaces, ABP, for melting, and their hand molding process handles castings up to 16 tons of gray cast iron and 8 tons of nodular cast iron. They manufacture a variety of components, including gearbox and pump housings. The foundry also boasts a fully equipped machining hall, including a grinding machine and a 3D measuring machine from Carl Zeiss. Their high-tech capabilities are complemented by an air-conditioned machining hall and advanced inspection tools, such as a 3D scanner for precise measurement, ensuring the production of high-quality parts. With a maximum workpiece size of 1,000 millimeters in diameter and 1,200 kilograms in weight, Cummins Foundry continues to serve various industries with precision and reliability. The Garutzpe heavy-duty lathe is a specialized machine designed for heavy cutting operations, including both roughing and finishing tasks. It is capable of handling demanding machining processes such as surface milling, keyway milling, interpolating milling, grooving, helical milling, and drum grooving, making it ideal for producing large, precise components. A standout feature of the machine is the additional visual unclamping conformation system, ensuring safety and accuracy throughout the machining process. The machine can also perform pocket milling and various other advanced milling operations with high precision, making it well suited for heavy-duty manufacturing in industries requiring durability and exceptional performance. Demiracablo is a technically oriented manufacturer specializing in the design and production of high-voltage and extra-high-voltage cable systems for energy transmission and telecommunications. The production facility is engineered to support large-scale industrial workflows with a 200,000 m² outdoor area dedicated to drum handling, conditioning, testing zones, and heavy-load logistics, which is essential for high-capacity cable manufacturing. From a technical standpoint, the company manufactures power cables in the 45 kV to 170 kV range, with a total annual output of approximately 4,000 km. These cables are produced using precisely controlled conductor stranding, insulation extrusion, and shielding processes to ensure consistent electrical performance, dielectric strength, and thermal stability. The facility is capable of producing cable drums weighing up to 50 tons, requiring reinforced handling systems and specialized tension-controlled winding equipment. PACCAR also manufactures metallic and fiber optic telecommunication cables. These products are engineered with strict dimensional tolerances, optimized conductor geometry, and protective layers to ensure signal integrity, mechanical resistance, and long-term durability under varied environmental conditions. A core technical capability is the production of 400 kV extra high voltage cables. This process involves advanced insulation systems, clean manufacturing environments, and multi-stage testing, including high-voltage electrical testing, partial discharge measurement, and insulation integrity verification. Each stage of production is monitored through quality control systems aligned with international standards. Through its emphasis on process control, high-voltage expertise, and heavy-duty manufacturing capability, PACCAR delivers technically reliable cable solutions for large-scale power transmission and communication infrastructure projects. At Caterpillar's Mapleton, Illinois foundry, engine block production is driven by strict metallurgical control and advanced casting technology to ensure long-term durability and performance. The process begins with the preparation of high-quality molten iron, carefully formulated to achieve the required strength, wear resistance, and thermal stability. Sand molds and cores are engineered with high precision to form complex internal passages, such as coolant jackets and oil galleries. Once poured, the molten metal fills the mold under controlled conditions to prevent defects and ensure uniform material distribution. After solidification, the cast blocks undergo shakeout, cleaning, and initial inspection. Advanced, non-destructive testing methods, including ultrasonic and X-ray inspection, are used to detect internal flaws. Dimensional accuracy is verified before blocks move to machining operations. Throughout the process, real-time data monitoring and statistical quality control are applied to maintain consistency across large production volumes. This disciplined approach allows Caterpillar to deliver engine blocks capable of withstanding extreme loads, high temperatures, and long service life in demanding applications.